Okay, so let's move on to chapter 3, which is measures of centered variations. So we're going to cover first half of chapter 3 since this is a long chapter. So first one, let's move on to the first measure of center, which is mean, right? So mean is a measure of center. And also it represents the center of data set, right? And the mean is the most important measure of center. It's also called arithmetic mean. So we see, for sample mean, we use x bar to represent it. So x bar, sample mean x bar equals summation of x divided by n. Here x represents the individual data value in the sample. M represents the sample size. For population mean, we use mu to represent it. Population mean mu equals summation of x over population size n. Let's get familiar with some symbols, right? First one is summation sign. Summation sign means addition of all data values. X represents each individual data value. N represents sample size. Small letter m represents sample size. Capital letter N represents population size. And first of all, let's look at examples. So Lee level in air at BMCC, we use milligram per cubic liter as a unit for that, and 1.5 being high. So the data is listed as 5.4, 1.1, 0.42, 0.73, 0.48, and 1.1. And this is a typical sample, so we use a sample mean formula. X bar equals summation of x divided by sample size n, which is equal to 5.4 plus 1.1 plus 0.42 plus 0.4773 plus 0.48 plus 1.1, dividing by 6, which is equal to 9.23 by 6. We get 1.538, and 1.538 is bigger than the benchmark 1.5, which means the average Lee level here is basically over the benchmark, meaning it will do some harm to our students. So the reason that occurs because we have an extreme value, which is outlier 5.4 here. So basically this 5.5 have a strong impact on me. And on a typical case, right, outliers always has very strong effect on me. And that's why people use the second measure of center, which is median, to measure that. Mean is good, but it's very sensitive to outliers. And large outliers have very dramatic effect on the mean. So the median is the middle value of the original data arranged in increasing order. So there's two scenarios here. If the sample size is odd, then exact middle value will be our median. If sample size is even, then we average the two middle values to get our median. And we use x tilde to represent the median. So let's look at an example, right? Data coming from Lee level in BMCC. So first of all, tally data. We arrange data in the increasing order. We get 0.42, 0.48, 0.73, 1.1, 1.1, 5.4. So our median x tilde equals to, since this data is, sample size is even, so we average the middle two. The middle two is 0.73 and 1.1. So we add this up, 0.73 plus 1.1 divided by 2. So we get a 1.93 by 2, which is equal to 0.915. And this is like way below the benchmark 1.5, so which is matches with the reality of the data set. So let's say we have an extra data point, which is we're adding 0.66 to this data set. We're going to get this data set, and then after reordering, we have 0.42, 0.48, 0.66, 0.73, 1.1, 1.1, 5.4. So the median here is 0.73 because this sample size is odd, 7, right? It's odd. So the exact middle value will be our median. So our median here is 0.73. So outlier has very strong in mean, but not so much on median. So sometimes you can use median to replace mean in order to get a good measure of center. Also, we have other ways of measure center, right? Like mode and the mid-range. So mode is the data value that occurs most frequently, and we use M to represent mode. And if two values appears most frequently, we call that this bimodal. If more than two values appears most frequently, we call that multimodal. If no value repeated, then there's no mode. The mode does not necessarily need to be numerical values. So let's look at this example. Example A, we get a 5.4, 1.1, 0.42, 0.73, 0.48, 1.1. So here 1.1 appears twice. So that is our mode, right? And second, example B, we get 27, 27, 27, 55, 55, 55, 88, 88, and 99. Both 27 and 55 appears 3 times. So we call that bimodal, 27, 55. And example C, we get 1, 2, 3, 6, 7, 8, 9, 10. And none of the number appears more than once. So we call that no more. And another way of measuring center is mid-range. So mid-range is equivalent to highest value plus the lowest value parenthesis divided by 2. Also, you can use maximum value plus minimum value parenthesis divided by 2. And outlier has very strong effect on mid-range because either highest value or lowest value could be outliers. So using the same example, right? Example A, our mid-range will be, the minimum value here is 0.42, maximum is 5.4. So add up these two numbers, divide by 2, end up with 2.91. Example B, the smallest value is 27, and the lowest value basically is 27. Highest value is 99, so adding 27 plus 99 parentheses by 2 give you 63. And example C, the lowest value is 1, and highest value is 10. So 1 plus 10 parentheses by 2, you get 5.5. More we use a lot with non-numerical value data. Let me give you an example, right? Survey shows students owns 84% of TV, 76% of VCR, 69% of CD player, 39% of video game player, 35% of DVD. And here the TV is the mode, because most people own TV, right? So here there's no possible way to find out the mean, median, or mid-range. So in this case, mode is the best measure of center for this. Also, I want to introduce a couple more formulas to compute a mean. Mean from frequency distribution. So mean x bar equals to summation of frequency, each individual frequency times x. X here means the midpoint of each class. And dividing by summation of frequency. Summation of frequency basically is total frequency, or you can say it's a sample size. And we also have a weighting mean. Weighting mean x bar equals summation of weight times x, dividing by total weight, summation of w. So measure the variation. Basically, variation measures consistency throughout the data. Also, we can use range to give us good idea of variation. So range equals to highest value minus lowest value. The standard deviation here, that's two formula, right? First formula is the standard formula, equals square root of summation of parenthesis x minus x bar, parenthesis square, divided by n minus 1. And that's a shortcut formula, which is standard deviation x equals square root of n times summation of x squared minus summation of x parentheses square divided by n times n minus 1. So here x represents the standard deviation, x represents each individual data value, x bar represents the sample mean, n represents the sample size. Let's take a look at an example of variation, right? So we have two types of errors. First one is precision errors. So precision errors look like this, and jungle errors. So basically, jungle error has more variation than precision errors, because the error changes more dramatically than the precision errors. So they have the same mean length but the different variations. And jungle errors has bigger variation because the error changes more dramatically. And let's first of all go through the first formula for the standard deviation, which is S represents standard deviation equals square root of summation of x minus x bar parentheses square divided by n minus 1. So that is standard deviation is a measure of the variation of all data from mean. And it can only be positive values or 0. And large deviation, large S, it could also increase dramatically with outliers. And it also has the same units as original data values. So the formula, the recipe to compute standard deviation is: first step, compute the mean. Second step, subtract mean from individual values. We get x minus x bar, right? Then we square the difference. We get x minus x bar square. And we add a square difference, which is summation of x minus x bar square, and divide by n minus 1. So we get that, and we take a square root as our last step. So let's take a look at example, right? So we have two data sets, bank consistency data set. And the object is waiting time. So we get a 654465. And bank unpredictable data set, we get 0, 15, 5, 0, 0, 10. So based on this recipe, so first of all we lay down all the data values. So we take a bank unpredictable data set, right? So it's 0, 15, 5, 0, 0, 10. Put it down vertically, and we compute a mean. So mean is basically you add up all the data values: 0 plus 15 plus 5 plus 0 plus 0 plus 10, give you 30, and divide by 6, we get 5, which is minutes. So we put in x bar here, we get and we subtract x from the mean, we get -5, 10, 0, -5, 5, -5, 5, and we square x minus mean, which is x bar squared. So 25, 100, 0, 25, 25, 25. And you add up those, you get 200. So our standard deviation equals square root of 200 divided by 6 minus 1, which is our sample size, minus 1. And which is square root of 40, which is equals to 6.3 minutes. And if we follow recipe, right? Let's take a bank consistency data as example. So we find a mean. So mean equals to 6 plus 5 plus 4 plus 4 plus 6 plus 5 divided by 6 equals to 5. And then we subtract each data value from the mean. We get 1, 0, -1, -1, 0, 1, 0. And we square each data. We get square each difference. We get 1, 0, 1, 1, 1, 0. And you sum up all this square difference, we get 4. And we divide 4 by 6 minus 1, which is 5. So we get 0.8. And we take square root of that value, we get 0.8. Square root of 0.8, we get 0.9 minutes. So compare 0.9 minutes to 6.3 minutes. So basically, bank unpredictable data set has a much bigger variation than bank consistency data set. All right, so we're gonna just finish here, and then we're gonna finish the rest of the in the second part of the